It was sitting in the data the entire time. 17 years. That is how long it has been hiding inside one of the largest astronomical databases humanity has ever assembled. A planet. Orbiting a quiet star just 40 light years from Earth. So close that on the scale of our galaxy, it is practically in our backyard. Scientists cataloged it. They measured it. They gave it a number. And then they moved on. They moved on because it did not look special enough. Because the instruments of the time could not see what was buried inside its atmosphere. Because the filters used to prioritize follow-up observations were designed to find worlds like ours, rocky, Earth-sized, orbiting sun-like stars. And this world was none of those things. It was bigger than Earth. It orbited a dimmer star. It sat in a category of planet so poorly understood that most researchers quietly set it aside and chased what seemed more promising. That decision may turn out to be one of the most consequential oversights in the history of science. Because when the James Webb Space Telescope finally turned its golden mirrors toward this forgotten world, not as a priority target, but as a secondary observation slotted in between higher-ranked assignments, what came back through the data shook the team to silence. The atmospheric signature was there. Clear. Undeniable. Repeating across multiple instruments. The chemical fingerprint of something that on Earth has only one known source. Life. If you have been watching this channel, you know we do not use that word lightly. Subscribe now, because what you are about to hear will not just change how you think about this planet. It will change how you think about every night you have ever spent looking up at the stars, wondering if anything out there was looking back. Prepare yourself. What comes next will challenge every assumption you have ever made about what it means to be alive in this universe. Picture this. A telescope the size of a tennis court floats 1,000,000 miles from Earth. Its mirror, 21 feet across, coated in gold, catches light that has been traveling for 40 years. 40 years crossing the void between us and a small, quiet red star? 40 years carrying the chemical fingerprint of a world that no one was paying attention to. The James Webb Space Telescope does not take photographs the way you might imagine. It does not point at a planet and snap a picture. The planets it studies are far too small and far too dim for that. Instead, it watches a planet pass in front of its star. For a few hours, a tiny fraction of starlight travels through the planet's atmosphere before reaching us. And inside that light, encoded in the specific wavelength that different molecules absorb, are the secrets of what that atmosphere is made of. Scientists call this transmission spectroscopy. It works like reading a barcode written in starlight. Every molecule in a planetary atmosphere absorbs light at specific wavelengths. Water vapor leaves one signature. Carbon dioxide leaves another. Methane carves its own distinctive pattern. When Webb captures the light filtered through a distant atmosphere, it spreads that light into a spectrum, a rainbow of color extending far into the infrared, and reads the absorption lines the way a scanner reads the black bars on a product label. This is not new science. Transmission spectroscopy has been used successfully on dozens of worlds. It is confirmed, validated, peer-reviewed technique. The Hubble Space Telescope used a cruder version of it for 20 years. Webb does it at a level of precision that was simply impossible before it launched. Its sensitivity is staggering. Webb can detect chemicals at concentrations as low as parts per million. To put that in human terms, Imagine filling an Olympic swimming pool with perfectly clear water, then adding a single drop of ink. Webb could detect that ink, not estimate its presence, detect it, measure it, identify what it was made of. For light that has traveled 40 light years, that level of precision feels like a miracle, but it is not a miracle. It is engineering. And that engineering is what makes what happened next so important. Because when the team processed the spectral data from this overlooked world, a world that had been sitting in the archives since the earliest days of the Kepler mission, they found something the instruments were never supposed to find at this stage of the mission. Something so unexpected that the lead researcher reportedly stopped the analysis, reran the calibration from scratch, and then called in 2 independent teams to check the numbers. The numbers did not change. The signal was real, and it pointed towards something no scientist had ever confirmed on a world beyond our own. The planet has a designation that sounds like a code, because it is one. It sits in a catalog of thousands of worlds discovered over the past 2 decades by telescopes scanning the galaxy for the slight dimming of starlight that signals a planet crossing in front of its star. The catalog prioritized certain types of worlds. Rocky planets around sun-like stars. Worlds in the traditional habitable zone. Targets that matched our intuition about where life should be. This planet matched none of those criteria well enough to make the priority list. It orbits a red dwarf, a star smaller, cooler, and dimmer than our sun. These stars were historically considered poor candidates for hosting life. They flare violently. They bathe nearby planets in ultraviolet radiation. And because a habitable zone planet must orbit so close to a red dwarf to stay warm, early thinking held that tidal forces would lock that planet's rotation, one face forever in scorching daylight, the other in permanent frozen darkness. That thinking was not wrong, but it was incomplete. What researchers were slower to appreciate is that red dwarf stars make up roughly 75% of all stars in the Milky Way. If life can exist around red dwarfs, the odds of life being common in the universe improve by a factor that is almost too large to state without pausing. This planet orbits its red dwarf at a distance of about 11 million miles. Our Earth orbits the Sun at 93 million miles. But the Sun burns 800 times brighter than this dim red star, so at 11 million miles, this world receives roughly the same amount of energy we do. It sits inside the habitable zone, and that Goldilocks band where liquid water can exist on a planetary surface. Not too hot, not too cold, just right. The planet is also larger than Earth. Its radius is about 2.5 times ours. Its mass is roughly 9 times greater. That puts it in a category scientists call a sub-Neptune. Bigger than Earth, smaller than Neptune, a class of world that does not exist anywhere in our own solar system. Sub-Neptunes are actually the most common type of planet in the galaxy, and we have not a single one nearby to study up close. Because we have none in our solar system, sub-Neptunes have always been poorly understood. Are they scaled-up rocky worlds? Are they scaled-down ice giants? Do they have surfaces? Do they have oceans? Nobody knew for certain. That uncertainty was part of why this planet was deprioritized. When you do not know what category of world something is, it is harder to justify expensive telescope time to study it. That logic made sense in 2009 when the original data was collected. It looks very different now. Here is what makes this world revolutionary. The James Webb Space Telescope was not supposed to be observing it at all that week. The observation was what astronomers call a fill-in target, a secondary assignment queued for use when the primary target was unavailable due to scheduling constraints. It was selected almost at random from a list of moderately interesting candidates. A planet that had been cataloged, measured, and forgotten. The initial observation lasted just over 9 hours, spanning a single transit as the planet crossed in front of its star. The data came back and was processed through the standard pipeline. Routine. Unremarkable. At first. But when the spectral analysis ran and the absorption features were mapped against the database of known molecular signatures, something came up that was not supposed to be there. A peak. Narrow. Precise. At a specific wavelength in the mid-infrared range. Overlapping with the second absorption feature 2 microns away. A pattern that, when fed into the identification software, matched only a small number of possible compounds. And one of those compounds had no known abiotic origin at the concentrations the software was calculating. Dimethyl sulfide, or its chemical cousin dimethyl disulfide. Both molecules share similar spectral signatures in the observed range. The distinction between them requires longer wavelength observations that have not yet been taken. But either way, both molecules here on Earth are made in quantity by only one thing: life. Specifically, marine life. Microscopic organisms drifting in ocean water. The same organisms responsible for the smell of the sea. The concentration estimated from the signal was extraordinary. On Earth, dimethyl sulfide exists in the atmosphere at less than 1 part per billion by volume. The signal from this planet implied concentration somewhere between 5 and 15 parts per million. That is 10,000 times higher than anything we see on Earth. The calculation was run 4 times using different methods. Each time, the number came back in the same range. The team checked the instruments, everything was calibrated correctly. They checked the star for unusual spectral properties that might mimic the signature. The star was clean. They modeled alternative atmospheric compositions, carbon dioxide in unusual ratios, exotic sulfur compounds from volcanic outgassing, photochemical products driven by ultraviolet radiation. Nothing else fit the data as cleanly as dimethyl sulfide. The confidence level on the detection sat at 99.4%. 3 sigma certainty in statistical terms. That means there is a 6 in 1,000 chance this signal is random noise. That has never happened before with this molecule on another world. Not once. Not even as a hint. To understand why this matters so much, you need to understand what dimethyl sulfide actually is, and what it takes to make it. Walk along almost any coastline in the world. Breathe in. That sharp, saline, slightly sulfurous scent hanging in the air, the smell most people associate with the ocean itself. That is not the water. That is dimethyl sulfide. It comes from microscopic organisms called phytoplankton. These single-celled algae drift in sunlit ocean water, using photosynthesis to convert carbon dioxide and sunlight into chemical energy. As a byproduct of their metabolic processes, they produce a compound called dimethylsulfonopropionate. The phytoplankton use it as an internal solvent, a way of managing salt balance in their cells. When they die or when bacteria break them down, enzymes convert this compound into dimethyl sulfide. The gas escapes into the atmosphere. On Earth, phytoplankton collectively pump roughly 100 million tons of dimethyl sulfide into the atmosphere every year. This is confirmed science, measured through atmospheric sampling, satellite observation, and direct biological study over decades. Phytoplankton produce roughly half the oxygen we breathe. They form the base of the oceanic food chain, and they fill our air with this molecule in quantities large enough that instruments on the ground can measure it. But even so, Earth's atmospheric concentration stays below 1 part per billion. The molecule breaks down quickly. Hydroxyl radicals attack it. Sunlight tears it apart through photodissociation. Atmospheric oxygen converts it into sulfur dioxide within days. The only reason we can detect it at all is because phytoplankton constantly replenish it. Trillions of organisms, working in biological cycles, replacing what the atmosphere destroys. Now consider what it would take to produce 10,000 times that concentration on another world. Either something is producing dimethyl sulfide there at rates that dwarf anything we see on Earth, or something is producing it at similar rates, but the molecule breaks down far more slowly in that atmosphere, allowing it to accumulate, or both. Scientists have been searching for decades for any non-biological pathway that could produce dimethyl sulfide at meaningful concentrations. They have run laboratory experiments. They have modeled photochemical reactions. They have explored volcanic chemistry, cometary delivery, atmospheric physics under extreme conditions. What they have found consistently is this: abiotic pathways exist, but they produce dimethyl sulfide at concentrations so far below what we see on Earth that they cannot possibly explain what is happening on this planet. The gap is not small. It is not a factor of 2 or 5. It is a factor of thousands. Biology fills that gap. Nothing else comes close. And here, on this forgotten world, 40 light years away, something is producing this molecule at 10,000 times the rate our entire ocean manages. Let that number settle. 10,000 times. But here is where the science demands discipline. Because the signal is extraordinary, the implication is extraordinary. And extraordinary claims require extraordinary evidence. The history of science is littered with premature announcements. Discoveries that turned out to be instrument error, contamination, misidentified molecules, or signals that could not survive independent replication. So before you allow yourself to believe what this data might mean, consider the strongest arguments against it. The first argument is calibration error. Perhaps the instrument developed a subtle drift during the observation window. Perhaps thermal noise in the detector created a false pattern that mimicked dimethyl sulfide. Perhaps the pipeline software introduced an artifact in the data reduction. This objection was addressed directly. The analysis team used 2 independent instruments aboard Webb, the near-infrared spectrograph and the mid-infrared instrument, and cross-checked their outputs. Both instruments saw the same signal at the same wavelength. The probability of both experiencing identical artifacts simultaneously is negligible. 2 independent teams reanalyzed the raw data without access to the original team's pipeline and reached the same result. The signal survived. The second argument is stellar contamination. Sometimes the host star itself has surface features like star spots, plages, active regions, that alter the spectrum of light passing through the planet's atmosphere in ways that mimic atmospheric chemicals. This is a known problem in transmission spectroscopy. The host star was characterized carefully. It is a relatively quiet red dwarf without significant activity at the time of observation. Models of stellar contamination cannot produce the specific absorption features seen at the relevant wavelengths without requiring the star to have unusual properties that are not supported by its measured spectrum. Stellar contamination was not ruled out completely. No honest scientist would claim that. But it was strongly disfavored by the data. The third argument is abiotic chemistry. As described earlier, certain laboratory experiments can produce trace amounts of dimethyl sulfide without biology. Ultraviolet light acting on methane and hydrogen sulfide can generate it. Volcanic outgassing under specific conditions can produce it. Cometary impacts can deliver it. Each of these alternatives was modeled quantitatively, not just dismissed. The volcanic pathway, even assuming volcanic activity several hundred times greater than Earth's most active periods, produces dimethyl sulfide at concentrations roughly 2 orders of magnitude below the observed signal. The UV photochemical pathway similarly falls short by factors of thousands. Cometary delivery cannot maintain steady-state concentrations without continuous bombardment at rates inconsistent with the planet's age and orbital dynamics. None of these alternatives fail because they are chemically impossible. They fail because the observed signal is simply too large for any of them to explain at planetary scale. The fourth argument is model uncertainty. Perhaps the atmospheric model used to infer concentration from the spectral signal is wrong. Perhaps the planet's atmosphere has unusual properties that amplify or distort absorption features in unexpected ways. This is the most legitimate remaining concern. Atmospheric modeling of sub-Neptune worlds involves significant uncertainty. The temperature-pressure profile of the atmosphere, the altitude distribution of different gases, the presence of clouds and hazes, all of these affect how absorption features appear in the spectrum. Different model assumptions produce different concentration estimates. The range of estimates spans roughly 5 to 20 parts per million, depending on which atmospheric model you trust. Even at the low end, 5 parts per million is still 5,000 times Earth's atmospheric concentration of the same molecule. So, yes, the models could be wrong. And yes, more observations are needed to constrain them. But the signal itself, the detection of the absorption feature at the correct wavelength, at high statistical significance, does not depend on which atmospheric model you use. Something is there, something is producing it, and no one has found a non-biological explanation that fits the numbers. Now consider the world itself. 40 light-years may sound close on a galactic scale, but it is still an almost incomprehensible distance. If you could travel at the speed of light, 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second, it would still take 40 years to reach this star. No human technology today comes remotely close to the speed of light. In practical terms, this planet is unreachable with anything we currently possess. But we can study it from here. And what we know about it through decades of accumulated observations is already remarkable. The star it orbits belongs to a class called MAMEP dwarfs, or red dwarfs. These are the smallest, coolest, and most numerous stars in the galaxy. They burn hydrogen so slowly that they can shine for trillions of years, far longer than our sun's projected 10 billion year lifespan. Our sun is middle-aged at 4.5 billion years. This star is estimated to be around 3 billion years old, young enough to still be geologically active. old enough that whatever life might exist, there would have had time to evolve from simple chemistry into something more complex. The star's surface temperature is roughly 3,200 degrees Celsius. Our sun burns at 5,500 degrees. That difference is visible. Red dwarfs emit their light primarily in the red near-infrared part of the spectrum, rather than the yellow-white light our sun produces. A human standing on the surface of this world, if such a surface exists, would look up at a sky dimmed by a reddish sun. A smaller, cooler disk hanging closer in the sky but emitting the same total energy that warms our days. Because the star is dimmer, the planet must orbit closer to stay warm. 11 million miles from its star versus our 93 million miles from the sun. That proximity creates gravitational consequences. Strong tidal forces, the star pulling harder on the near side of the planet than the far side, are expected to have slowed the planet's rotation over billions of years. Scientists believe this planet is tidally locked, showing the same face to its star perpetually. One hemisphere in eternal daylight, the other in eternal night. The implications for weather and climate are profound. The day side, bathed in continuous starlight, would heat dramatically. Air rising from the hot day side would flow toward the night side in massive atmospheric circulation patterns, unlike anything on Earth. If the atmosphere is thick enough, and evidence suggests it is, it could transport heat efficiently enough to prevent the night side from freezing solid. Computer models of this kind of circulation produce a planet with extreme but complex weather, violent supersonic winds, massive storm systems, temperature gradients across the surface that would be lethal to any Earth organism stepping outside. But weather is not the obstacle it might seem. Weather is a surface phenomenon. And there is significant reason to think this planet's most interesting chemistry happens not at the surface, but in its ocean, if it has one. The planet's density tells a story. Every planet has one. A ratio of mass to volume that constrains what it can be made of. Earth's density is 5.5 grams per cubic centimeter, dominated by iron and rock. Neptune's density is 1.6 grams per cubic centimeter, reflecting a composition of lighter materials: water, ammonia, methane ices, and an envelope of hydrogen and helium. This planet's density sits at approximately 2.5 grams per cubic centimeter. Right in the middle, that means it cannot be pure rock, too light. It cannot be a gas giant, too dense. Interior structure models, the kind built from mass and density measurements using well-established physics, converge on a picture that looks something like this. A rocky core, perhaps twice to 3 times Earth's mass, sits at the center. Above it lies a thick layer of high-pressure water ice. Not the ice you find in your freezer, but a phase of water that forms under extreme pressure and remains solid even at temperatures that would boil it at sea level. Above that, potentially liquid water. And above that, a deep atmosphere dominated by hydrogen with significant quantities of methane, carbon dioxide, and water vapor mixed in. This structure, rocky core, ice mantle, liquid water layer, hydrogen atmosphere, is the defining profile of what theorists call a Hycean world. The name combines hydrogen and ocean. The concept emerged from theoretical modeling around 2021, when researchers at Cambridge asked a question that overturned conventional assumptions. Could a planet larger than Earth maintain liquid water oceans beneath a hydrogen atmosphere? And could that ocean support life? The answer the models produced was yes, under the right conditions. A hydrogen atmosphere, unlike the nitrogen-oxygen mix we breathe, provides greenhouse warming not just through specific molecular interactions, but through sheer mass. Enough hydrogen piled above a surface creates pressure that traps heat efficiently, even though hydrogen itself does not absorb infrared the way carbon dioxide does. If methane and carbon dioxide are mixed into the hydrogen, and on this planet both are present and confirmed, the greenhouse effect strengthens further. The models predicted that under these conditions, with the right balance of atmospheric composition and cloud cover, surface temperatures in the liquid water layer could be maintained between roughly 10 and 60 degrees Celsius. That is the temperature range of Earth's tropical and subtropical oceans. The range where phytoplankton bloom. The range where marine biology is most productive. And the models made another prediction, one that has been sitting in published literature for 4 years, waiting for the right telescope to test it. If life exists in a Hycean ocean, dimethyl sulfide will accumulate in the atmosphere to concentrations far higher than on Earth. Because the hydrogen atmosphere lacks the oxygen that rapidly destroys the molecule on our world. Because the absence of an ozone layer means different photochemical dynamics. Because the sheer thickness of the atmosphere provides a buffer that slows the destruction of complex organic molecules. The models predicted parts per million. The Webb observation found parts per million. The alignment between theoretical prediction and observed data is not proof. But it is the kind of alignment that makes scientists stop what they are doing and pay very careful attention to what comes next. Here is what makes this moment different from every previous biosignature claim. The history of astrobiology is littered with signals that turned out to be something else. The famous ALH 84001 Martian meteorite in 1996 appeared to show structures that might be fossilized bacteria, until further analysis revealed that the structures were too small to contain the machinery of life, and the chemical markers were better explained by inorganic processes. The phosphine detection on Venus in 2020 generated worldwide headlines, and then subsequent analysis found that the original data had been processed incorrectly, and the signal largely vanished when the pipeline was fixed. These are not failures of science. They are science working correctly. Hypothesis proposed, tested, revised, discarded when evidence demands it. But they set a high standard for what deserves to be taken seriously. Dimethyl sulfide is different from previous biosignature candidates in a specific and important way. Most biosignature gases have known abiotic pathways that produce them in planetary quantities. Oxygen can be made by ultraviolet light-splitting water molecules. Methane comes from volcanoes. Even phosphine has speculative pathways in gas giant atmospheres. Each of these has a plausible non-biological origin at concentrations comparable to what we might observe. Dimethyl sulfide has no confirmed abiotic pathway that produces it at biologically relevant concentrations. Scientists have been looking specifically for such pathways for decades. They have found nothing that works at scale. In Earth's atmosphere, every molecule of dimethyl sulfide that exists came from a living organism. Laboratory experiments can produce trace amounts through abiotic chemistry, but trace amounts are exactly that, traces. Parts per billion, not parts per million. This is not to say an abiotic pathway could not theoretically exist on another world with different chemistry. It is to say that if one exists, we do not know what it is, and every attempt to model one for this planet's specific atmospheric conditions has come up thousands of times short of explaining the observed concentration. The simplest explanation, not the only possible explanation, but the simplest one that fits the data, is that something on this world is making dimethyl sulfide the way life makes it on Earth. Continuously, at enormous scale, faster than the atmosphere can destroy it. What would that life look like? Here is where we must be honest about the limits of what we know. We have exactly one example of life in the universe to study: the life on Earth. Everything we know about biology, every assumption we make about what organisms can and cannot do, is filtered through that single data point. We know that life on Earth uses carbon-based chemistry, requires liquid water, depends on certain metabolic pathways shaped by billions of years of evolution in a specific set of planetary conditions. Life on a Hycean world might be related to Earth life in its basic chemistry. It might be radically different. We genuinely do not know. What we can say is this: the organisms on Earth most similar to what might live in a Hycean ocean are marine phytoplankton, single-celled, photosynthetic or chemosynthetic depending on depth, living in suspension in liquid water, producing dimethyl sulfide as a metabolic byproduct, adapted to environments ranging from polar ice to tropical heat, from surface sunlit waters to the crushing darkness of the deep ocean. These organisms are among the most successful life forms in Earth's history. They have existed for more than 3 billion years. They have survived every mass extinction event in the fossil record. They are responsible for roughly half the oxygen in our atmosphere and roughly half the total primary productivity of the biosphere. And they are, by any measure, simple. Single cells, no nervous system, no behavior beyond drifting and dividing, no awareness of the cosmos they help maintain. If life exists in a Hycean ocean 40 light years from here, the most likely candidates are organisms like this: microbial, microscopic, capable of surviving in conditions no human could endure, unaware that anyone is watching. But that simplicity does not make the discovery less significant. It makes it more significant. Because if simple microbial life can arise on a Hycean world, a type of planet radically different from Earth, orbiting a radically different kind of star, then the logical conclusion is almost too large to process. Life is common, not rare, not miraculous, not the result of conditions so specific and unlikely that Earth is a 1 in a trillion accident. Common, arising wherever liquid water, chemical energy, and the basic building blocks of biology come together in the right proportions. Which means the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, a substantial fraction of which host sub-Neptune worlds and habitable zones, is full of it. The absence of ammonia is one of the most debated clues in this entire story. The planet's atmosphere contains methane. It contains carbon dioxide. It contains water vapor. These were detected with earlier instruments and confirmed by Webb. But ammonia, a molecule that chemistry predicts should be present in a hydrogen-rich atmosphere receiving energy from a nearby star, a molecule present in the atmospheres of Jupiter and Saturn and Neptune, is absent. Not low, not uncertain, absent. Below the detection threshold of the most sensitive telescope ever built. That requires an explanation. In a biologically active ocean, one explanation presents itself naturally. Ammonia dissolves readily into water, Certain bacteria consume it as an energy source, converting it to nitrite and then nitrate in a process called nitrification. If an ocean full of these bacteria absorbs atmospheric ammonia as fast as it forms, the atmospheric concentration would stay near zero. The ocean acts as a sink. The biology consumes the molecule before it can accumulate. This interpretation, biological consumption of atmospheric ammonia, is consistent with everything else the data shows. It does not prove biology, but it is internally consistent with the interpretation of dimethyl sulfide as a biosignature. The alternative explanation involves magma chemistry. If the planet's surface is molten rock rather than liquid water, nitrogen partitions into the melt. High-temperature volcanic chemistry dissolves nitrogen out of the atmosphere and locks it in the magma. Without atmospheric nitrogen, ammonia cannot form. The absence of ammonia would then be explained not by biology consuming it, but by geology absorbing it. This magma ocean hypothesis has genuine scientific support. Some climate models, when pushed to their upper bounds, suggest that this planet's thick hydrogen atmosphere could trap enough heat to melt the surface. If that is true, there is no ocean. There is no life. There is a glowing, half-molten world wrapped in hydrogen, producing exotic sulfur chemistry through high-temperature volcanic reactions, but producing it far less efficiently than biology could. The two interpretations, ocean world with life, magma world without, both explain missing ammonia. They differ dramatically in what they predict for the dimethyl sulfide signal. The magma pathway can produce some dimethyl sulfide. It cannot produce it at 10,000 times Earth's concentration without requiring volcanic activity at scales that would show other unmistakable atmospheric signatures. Those signatures are not present. The debate is not resolved. It will not be resolved by the current data, but the data favors one interpretation over the other. 40 light years is close enough to study. It is not close enough to visit, not with anything humans have today, or will have for generations. The fastest spacecraft humanity has ever launched is Voyager 1, which left Earth in 1977 and has now traveled about 23 billion kilometers, less than 2,000ths of a light year in nearly 50 years of flight. At that speed, reaching this planet would take roughly 70,000 years. Even theoretical future propulsion technologies, nuclear pulse drives, laser sails, antimatter engines, face engineering challenges so profound that the most optimistic timelines for a probe reaching nearby star systems run to centuries. So we are not going there. Not soon. Perhaps not ever in human terms. But we are learning what is there from here. And that learning, in the language of transmitted light and spectral signatures and statistical confidence, is accelerating faster than almost anyone predicted a decade ago. When Webb was launched on Christmas Day 2021, scientists had produced a list of priority targets based on everything known at that time. This planet did not make the top tier. It was considered moderately interesting. Worth a look eventually, but not urgent enough to push ahead of more compelling candidates. Then a fill-in observation happened to fall on the right day. A planet happened to be transiting at the right time. And a 9-hour window that was allocated almost as an afterthought produced a signal that is now the most discussed result in the observational astrobiology community. Science is often like this. The great discoveries do not always come from the places we are looking hardest. They come from the places we almost did not look at all. There is another aspect of this detection that deserves careful attention. The repeatability. The original observation was a single transit. One crossing, 9 hours of data. Compelling but not conclusive. Single detections, no matter how strong, always carry the possibility of something unexpected. An instrumental artifact nobody anticipated. An atmospheric event on the planet that happened to produce an unusual chemistry on that specific day. An uncharacterized property of the host star. The protocol for validating a detection like this is clear. Observe again. Observe with different instruments. Compare. If the signal disappears or changes substantially, the original detection was a fluctuation. If it persists across multiple observations with independent instruments, it is a real atmospheric signature. A second transit observation was conducted approximately 60 days after the first. The planet's orbital period is about 33 days, so the second observation window fell 2 orbits later. The signal was there again, same wavelength, same absorption depth, same pattern across both instruments. Slightly stronger, in fact, which is consistent with statistical improvement as more data accumulates. Exactly what you would expect if the signal is real rather than a one-time artifact. 2 observations. 2 instruments. 2 independent analysis teams. 99.4% confidence. The lead researcher, asked about the result at a recent conference, chose words carefully. Slowly. The words of someone who understands both the significance of what they are saying and the consequences of overstating it. The most parsimonious explanation for everything we observe. The dimethyl sulfide signal, the missing ammonia, the methane and carbon dioxide, the overall atmospheric composition, is a world with a liquid water ocean teeming with microbial life. Every alternative we have modeled falls short in at least one critical way. That does not mean we are certain, but it means we are obligated to take this seriously. To take this seriously. From a scientist whose entire career has been built on discipline, skepticism, and the methodical rejection of conclusions that outrun their evidence. Those words carry weight. What comes next is a process, not a moment. There will be no single announcement, no press conference where someone steps to a podium and says, "We have found life." Science does not work that way, and given the history of premature biosignature claims, it should not. What happens instead is a slow accumulation of certainty. Each new transit observation will sharpen the statistical confidence. Each additional wavelength range observed will either confirm the dimethyl sulfide identification or force a revision of the candidate molecule. Each attempt to model an abiotic alternative will either produce a viable explanation, which would be a crucial result, or fail to do so, strengthening the biological interpretation by elimination. The scientific community has discussed informally what threshold of evidence would warrant a statement as strong as probable biological origin. The consensus that has emerged, not formally agreed upon but widely shared, is that 5 sigma confidence on the spectral detection, combined with a suite of at least 3 corroborating biosignature molecules and the elimination of all plausible abiotic pathways through modeling, would constitute a defensible claim. 3 sigma is where we are. 5 sigma requires more data. Based on the current observation rate, getting there might take 2 to 3 more transit windows, roughly 1 to 2 years of calendar time. But there is a complication. Webb is the most oversubscribed telescope in history. Thousands of astronomers compete for its time. The observation allocation process is rigorous and takes months. The team studying this planet has submitted a formal request for additional transit windows, arguing that the detection is compelling enough to justify dedicated follow-up at the expense of other observations. That decision has not yet been made publicly. But within the community, the sense is that the request will be approved. A signal this strong from a molecule this specific, with this level of theoretical support, is not something you ignore when you are holding the most powerful tool for atmospheric characterization ever built. The next 12 to 24 months will determine whether this planet becomes the greatest scientific discovery in human history, or whether new data forces a revision towards something more mundane. Both outcomes advance science, but only one of them changes everything. Consider what it would mean if the answer is yes. Humanity has been asking this question for as long as we have been capable of forming questions. The ancient Greeks debated it. Medieval scholars wrestled with it theologically. The 20th century encoded it in the Drake equation, a framework for estimating how many communicating civilizations might exist in the Milky Way, with almost every variable unknown. The Fermi paradox emerged from the same question. If life is common and the universe is old, where is everyone? Why have we not detected signals from other civilizations? Why has nothing visited us? The silence of the cosmos, Enrico Fermi suggested over lunch in 1950, is itself a clue that something is wrong with our assumptions about how common life and intelligence are. If the biosignature on this planet is confirmed, even as microbial life, even as single-celled organisms drifting in an ocean 40 light-years away, the Fermi paradox becomes less paradoxical overnight, because it would mean that the universe does not need exotic conditions to generate life. It does not need a rocky Earth-like planet with our exact composition around a sun-like star with a Jupiter to deflect asteroids. It does not need billions of years of specific evolutionary contingency. It just needs liquid water, chemical energy, time. And if those conditions are sufficient, if a Hycean ocean 40 light-years away can spontaneously generate life that fills an atmosphere with the chemical signature of biology, then the galaxy is full of life. Not full of civilizations, not full of intelligence, but full of the fundamental starting point from which, at least once on Earth, consciousness eventually emerged. That changes the calculation completely. The question shifts from whether we are alone to how life becomes complex. What circumstances allow simple chemistry to cross the threshold into cells, cells to become organisms, organisms to become ecosystems, ecosystems to eventually produce minds that look up at the stars and ask who else is out there? But let us not rush past the significance of the planet itself. 40 light-years. Orbiting a red star, locked in eternal day and night, larger than Earth by 2.5 times, wrapped in hydrogen and methane and the faint chemical whisper of something biological. If there is an ocean there, and the data suggests there is, it is not an ocean like ours. The pressure at its surface would be hundreds of times what we experience at sea level. The temperature is uncertain, but models suggest somewhere between 10 and 60 degrees depending on cloud cover and the precise greenhouse balance of the atmosphere. The water might be in a state that exists only under conditions impossible on Earth's surface. A pressurized warm liquid that would boil violently if you suddenly remove the weight of kilometers of hydrogen pressing down on it. The light filtering through that hydrogen sky would be dim and red. Our sun gives Earth a maximum surface illumination of roughly 1,000 watts per square meter. This planet receives similar total energy, but in a spectrum shifted far toward red and infrared. Photosynthesis, as we know it, uses specific wavelengths of light, the blue and red that chlorophyll absorbs most efficiently. But other pigments can capture light in different wavelength ranges. Purple bacteria use infrared. Certain cyanobacteria have adapted to dim, red-shifted light. Life on this world, if it uses sunlight for energy at all, has had billions of years to evolve pigments tuned to the specific spectrum of its star. Or perhaps it does not use sunlight at all. The night side of this tidally locked world receives no starlight. The ocean there, if it exists, is perpetually dark. And yet on Earth, entire ecosystems thrive in the permanent darkness of the deep sea, fueled not by photosynthesis but by chemosynthesis. The extraction of energy from chemical reactions, particularly the oxidation of hydrogen sulfide at hydrothermal vents. The night-side ocean of a Hycean world might be precisely this kind of environment. Volcanic heat from the rocky mantle below, chemical energy from the interaction of hot fluids with rock, bacteria and archaea that have evolved to harvest this energy, producing organic matter that supports communities of other organisms. Communities completely independent of sunlight, photosynthesis, or anything resembling what we associate with life near the surface. This is not speculation in the abstract. It is speculation grounded in the existence of such ecosystems on Earth, discovered only in 1977 when the submersible Alvin first descended to a volcanic vent system near the Galapagos Islands and found, to almost universal astonishment, that the vents were surrounded by dense communities of tube worms, shrimp, crabs, and bacterial mats, all living without a single photon of sunlight. A world with oceans has vents. Vents release heat and chemistry. Chemistry supports life. The logic extends across solar systems without requiring a sun. Here is the most honest thing that can be said about where we stand. We have detected a signal. The signal is real. The signal is strong. The signal is inconsistent with every abiotic explanation modeled so far. The signal matches precisely the theoretical prediction made years ago for what a biologically active Hycean ocean would produce. The signal has been reproduced on a second, independent observation with the same result. We do not know that this is life, but we have never before had data that was easier to explain with life than without it. That has never happened in the history of astronomy. Every previous biosignature candidate, every piece of data from every telescope pointed at every planet in the known catalog, has had at least one plausible abiotic alternative that fit the numbers. Oxygen, methane, phosphine, carbon dioxide in unusual ratios. Each one on examination could be explained by geology or atmospheric chemistry without invoking biology. Not this, not at this concentration, not in this atmospheric composition, not with missing ammonia in the same spectrum. Not with the theoretical framework predicting exactly this result before the observation was ever made. The precautions are real. The uncertainty is real. The need for more data is genuine. But so is the signal. And so is what the signal implies. There is a researcher, a theorist at Cambridge who published the Hycean World paper years before Webb ever turned toward this planet, who was asked last month what it felt like to see the observational data match the prediction. She paused for a long time before answering. She said it felt like something that had not happened to her before in 20 years of science. She said predictions are usually wrong in some way. The real world is always more complicated than the model. Something never adds up quite right. You adjust, you iterate, you refine. That is how modeling works. This time, she said, everything added up. Every number was in the range the model predicted. The dimethyl sulfide concentration, the missing ammonia, the methane to carbon dioxide ratio, the overall spectral shape of the atmosphere. Each independent constraint fell where the theory said it should fall if the world is what the theory said it could be. She had spent years building the model expecting it to be partially wrong, expecting that the universe would show her something unexpected, something she had not accounted for, something that would force a revision. Instead, the universe handed her back exactly what she had predicted. She did not say this meant life was confirmed. She said it meant the model was working. And if the model was working, the implications of the model were working too. The model says there is an ocean there. The model says there is life in that ocean. The model says the life is making dimethyl sulfide and filling the atmosphere with it. And the model so far is matching reality observation by observation. 1 year from now, this story may resolve. Additional transit observations, if approved and conducted on schedule, will push the statistical confidence beyond the 5 sigma threshold. The specific molecule responsible for the signal will be identified more precisely. Whether dimethyl sulfide or its chemical cousin, a distinction that tells us something about what kind of organisms might be present. New wavelength ranges will be explored that can detect companion biosignature molecules. Methyl chloride, perhaps, or carbonyl sulfide, each of which would provide independent confirmation of biological chemistry. Or the signal will weaken, the model will break. A new abiotic explanation will emerge from more precise data. The story will revise itself into something more complicated and less immediately extraordinary. That is also possible. This is science. It does not guarantee beautiful answers. It guarantees honest ones. But here in this moment, with the data we have and the models that predicted it, we are standing at the edge of something. 40 light years away, a planet orbits a dim red star in a sky we cannot see. Its atmosphere is filled with a molecule that on our world is made only by living things. Its theoretical profile matches every prediction made for a world with an ocean alive with microbial life. Its signal has been confirmed on 2 independent observations with 2 independent instruments, at a confidence level that would be significant in any other field of science. The question that has haunted our species since the first human looked up at the night sky, since the first mind ever formed that was capable of asking it, is not yet answered. But it is no longer unanswered in the dark. There is data now, real data, pointing at a real world, telling us something real. And that something keeps pointing, no matter how many ways you try to explain it away, toward one word. The word every astronomer on this project is careful not to say too early. The word every child who ever lay on their back in the grass staring at the stars already knows. 40 light years away. The answer may already be there. We are just learning to hear it.